All right, so what we're going to be looking at now today is we're going to be looking at work problems, and these are what we call constant force problems. This is a subcategory of work problems. We'll look at some other work problems in just a little bit, but we're going to utilize these in order to create the foundations for understanding how work works. There you go. Basically, what work is, all right, is from the simplest perspective, work is going to equal the force times the distance traveled, where force is going to end up equaling mass times acceleration. Okay, work is going to be generally measured in joules, which is also sometimes called newtons per square meter or meter squared, and then force is going to be measured in newtons. And so we've got some basic equations that we're going to be utilizing, and we're going to be utilizing those equations then to build up more and more complex work problems. All right. Right now, those equations look very straightforward. They look like very straightforward physics equations. What we're going to be doing is we're going to be asking ourselves questions about what happens when, say, for example, the force changes depending upon the distance, right? And when that happens, that's when integration is going to end up getting involved. So let's look at a basic weight problem, or excuse me, work problem. Suppose that we have a cable that weighs 2 pounds per square foot and it hangs from a 100-foot building. How much work is required to lift the cable to the top of the building? So let's imagine that we have the building, okay, and it's 100 feet high. And what I've got is I've got my cable, and my cable is going to come down here to the bottom. And it's a heavy cable, all right? And what we have here is we have that its weight, all right, is 2 pounds per square foot. Excuse me, not per square foot, but 2 pounds per foot. Now, what you'll notice here is you'll notice that we don't have this. This is not newtons, okay? But weight, in terms of pounds, is in fact a force. All right? For those of you who don't know any physics or haven't gotten through some physics, what you should know is that weight actually is a force, pounds. All right? So what we're going to be doing is we're going to be figuring out, right, the force exerted on the rope and how far it actually moves. Its displacement. And we're going to do that using some calculus. So let's imagine that I've got an ith interval, okay? So actually, first, let's do this, and let's break up. We're going to break up this rope into n subintervals, all right? Just like we've done everything else. And we're going to imagine this here is our x-axis, all right? That line is our x-axis. So here's 100 feet at the bottom, and we're going to make 0 to be the top. And the reason why we're going to do that is because as we raise the rope or the cable, what we're going to do is that the cable ends up getting lighter and lighter and lighter as we move it up until we hit 0, in which it actually has no force acting on it because there's no cable out over the top of the building. Okay, so that's why we're actually going to set it up this way. We're going to make 0 at the top and 100 at the bottom. Okay, and so now what we're going to look at, and so our delta x is going to equal 100 divided by n, right? Because we have n subintervals, just like we've been doing in all of our calculus thus far. So we've got those n subintervals, and we're going to look at this ith interval. So what we've got here now is we've got this point right here is xi star, and that's some interval inside of this, that's some point in between xi and xi minus 1. Okay, so it's somewhere in there, in between those two. And so what we want to get here, and this thing here is delta x, all right? So that's a particular distance that our object is going to travel. Now, the force that is acting upon this like ith interval, all right, is going to be approximately, so it's close to 2 times xi star, okay? All right, xi being a number of feet, okay? So you have 2 pounds per foot times a number of feet, so you get a number of pounds, and that's your force. And the distance or the displacement that we're going to move that object or that particular part of the object, okay, is going to end up being delta x. So what we're going to get here is that our work for that ith interval, wi, is going to be 2 xi star times delta x. So that's what it's going to look like. 2 xi star times delta x. And what we know is if we add up all of these, we've got n of them, we're going to get the sum, I equals 1 up to n of the wi's, and so that's 2 xi star times delta x. And now what I want to do now next is I actually want to, I'm going to let that limit. I'm going to make each interval very, very small. So it's going to give me a better and better and better estimate by making each interval small. And how I'm going to do that is by taking the limit as n approaches infinity of this sum. And that ends up giving me the integral now from 0 to 100 of 2x dx. We've seen that before now a lot, right? Okay, so what we've done is we've taken that force, right, and we've taken the force function and we've integrated it, okay, and by integrating it, that actually multiplies it over the distance and allows that force to actually vary over the entirety of the distance of the building. So this ends up giving me x squared from 0 to 100, and this is then going to equal 10,000, okay, foot pounds. Okay? Or foot pounds, excuse me, foot pounds, not foots per pound, it's foot pounds. And that is our measure of work. That's the work that's done. Okay? So basically, the trick here is for us going to be able to find the force, right? Then we end up multiplying that by the delta x, right? Separating out or that amount of displacement is that little delta x from wherever we're going from the beginning to the end, and then that ends up giving me, when I integrate, it ends up giving me my work for the entire building. All right, let's take a look at another example in order to help illuminate a little bit more what we've been talking about and help you to set up work problems when there's some kind of variation, okay? And in particular, help us to understand what does it mean when we say something like force times the amount of displacement or distance traveled. So let's find the work done lifting a 20-pound object from the ground to the top of a 55-foot building if the cable used weighs 2.5 pounds per foot. So let's imagine that what I have now, okay, I've got my building again. I've got 55 feet here, okay, and I have my cable, and it's coming from the top. And now what I've got is I've got a constant weight here, the constant weight of 20 pounds. That's always on the bottom, okay? And what I'm going to do is I'm going to break up my line into n components. So that's each one's going to be 55 divided by n, right? That's how long each one is going to be. And let's take a hypothetical xith, or take the ith interval, okay? So we've got this one. It's delta x in length. It's the ith interval, and somewhere in there it's got xi star as one of the points in there. So what we're going to do is we're going to break up the force here into the force that the cable is exerting and the force of the object, okay? The force that the cable is exerting and the force of the object. So we first look at the cable, and the cable is going to be, it's got that 2.5 pounds per square foot, and we've got times xi star. That's how far away it is from the top, okay? So that's its force. Then the force of the object, the rock or the weight that's at the bottom of it, is just simply 20, all right, because it's constant, right? And remember what we said at the beginning, pounds are another way of expressing force when we're using standard metrics, okay? So there's my cable, there's my object. Now what I'm going to do is I'm going to ask myself, well, the work done on the ith interval is going to be approximately, okay, 2.5 xi star plus 20, and then we're going to multiply that by delta x, because that's the amount of displacement, the amount of distance that we're going to move the object, okay? So what you can see here is we've basically just broken up our forces. We've thought about, okay, well, what's the force, right? And how do I break up the forces in order to, give me a sense of the total work done by somebody who's standing at the top of the building. So now I'm going to add up all of those. So I'm going to get I equals 1 up to n of those wi's, 2.5 xi star plus 20 times my delta x. And what we'll then do is we will take the limit as n goes to infinity. So we'll make each one of those intervals very, very, very small, right? We're going to make them tiny, 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 okay, to go from an approximation to the actual value of the work. So this is now, when we take that limit as n approaches infinity, that's going to then give me my integral, okay? And so that's going to then go from 0 to 55, because that's from the bottom of the building, or yeah, from the bottom of the building to the top of the building. And that'll give me 2.5x plus 20 dx. All right, so when we go in, we take that limit as it approaches infinity, we get the integral, right? Our delta x's become a dx, just like we've been seeing. So now this gives me now 1.25 x squared plus 20x, and we're going to evaluate that from 0 to 55. And when we do that, what we end up getting is 4,881.25 foot-pounds. And that's our work. Okay? So this gives us another variation, something that we can kind of think about as we are setting up our work problems, when what we're looking at is we're looking at varying forces. What we're going to look at in just a second is we're going to ask ourselves, well, what happens if we vary our distances? So now let's take a look at a different problem, all right, with maybe some different, just a kind of a slightly different idea. Let's say, for example, that we want to find the work done if you're lifting an object that weighs 150 pounds from the top of a building that is 100 feet high. If we lift the object from 30 feet in height to 90 feet in height, and the chain holding the object weighs 0.4 pounds per foot. Okay, so now what I want to do is I want to imagine my building. Okay, I've got my building, and again, I've got 0 at the top. Okay, and I've got at the bottom, I've got 100. Okay, we get 0 to 100. The weight at the bottom is now 150 pounds. All right, and we've got that the weight of the chain is 0.4 pounds per foot. But now what I want to get is I'm going to go from 30 feet to 90 feet. Okay, so I'm going to go from 30 to 90. And so because I'm doing that, that changes my problem pretty significantly. Okay, it's going to end up changing my problem pretty significantly. Let's first think about the object. Now the object, okay, is going to be, it's going to travel from 30 feet to 90 feet. Okay, we just want to know that. So once it hits 30 feet, we maybe even can imagine that it's sitting there at 30 instead. It's been lifted up there. It's going to go from 30 to 90 feet, and its force is going to end up being constant. Okay, so its force is going to be constant, and its force is 150 pounds. Okay. Now, when we think about the chain, on the other hand, the chain is going to vary depending upon where it's located on the building. Okay, where it's going to be located on the building. So what we want to do is we want to account for that variation in terms of the where the chain is actually located. All right. So we're going to start out with 0.4. That's the number of pounds per foot, and then what we're going to do is we're going to multiply that by the distance that the chain is away from the ground. Okay, or excuse me, the distance that the chain has to actually move up to the top of the building. Pardon me. So that's actually going to be 100 minus x. And the reason why is to imagine I've got 100 here. Okay, there's the 100 feet. And at 30 feet, okay, at 30 feet, what I've got is I've got 70 feet worth of cable. Okay, so at 30 feet, I've got 70 feet worth of cable. Excuse me. And at 90 feet, I've only got 10 feet worth of cable. So the amount of cable that I actually have, right, that distance that the object is away from the top is going to be 100 minus x. It's not actually going to end up being x. All right. In previous instances, we could just use x because we were going up the entirety of the length of the building. That's not what's happening in this case. Okay. So what we're going to do now is we're going to take these two. These are the equations for our force, right? We'll call this maybe an f of x1, and this we'll call f of x2. And we add those two together. So our integral now, all right, and this is just going to end up being the general integral that we use, is going to end up being, in this case, we're going to go from 30 to 90, okay, and we account for that using the 100 minus x, all right, it'll be 150 plus 4, or 0.4 times 100 minus x, and all of that delta x, or not delta x, but excuse me, dx. Okay, so it's my f dx, f of x dx. And so this ends up equaling 150x plus 40x minus 0.2x squared, evaluated from 30 to 90. and that ends up equaling 9,960 foot-pounds. And that is how we find something that looks like that. All right. One of the key issues that we have whenever we're dealing with these kind of problems, where we're not actually moving the chain all the way up the building, or where we only want to look at a variable force in some kind of sub-interval of a larger interval, is to consider where is 0 and where is the end of our larger interval, right? Okay, in this case, the 100. And and when we do that, oftentimes what we're going to have to change that distance utilizing the top distance minus wherever we are at on the building or on whatever object we're looking at. All right, so let's take a look at another subcategory, a simple subcategory of work problems that have to do with these things called spring masses. All right, so let me draw a picture of a spring mass. A spring mass looks something like this. We've got something that's been moored to a wall, and you've got the spring, okay, and it's got a resting length. That is that if no force is being exerted upon the spring mass, then it's going to be of a certain length, okay? Call it K, call it X, actually we won't call it a K, call it R. Okay, that's our resting length. And then what happens is that we will extend it, we'll displace the spring, okay? We're going to displace the spring by, right, an amount D, okay? We got the displacement of the spring D, okay? So there's an amount of force that's going to be needed in order to displace the spring, that D amount, okay? All right, and that is called the spring mass constant. That amount of, well, actually, the amount of force is going to be dependent upon something called a spring mass constant. All right, so that force is going to equal K times P, okay, or excuse me, KD, where D is the amount of displacement, and K is some constant. And the constant is just really going to depend upon how tight the spring is. Tighter the spring is, the more force that's needed in order to pull the spring out to displace the spring. So we're going to be finding K each and every time. That's going to be one of the things that we're going to end up doing. So we're going to utilize this fact because we have what we know is we have this thing. What we now know is that the work that is done, W, is going to equal the integral of A to B, which is the amount that we're actually stretching, the amount that we're going to displace, A to B of f of x dx, our force times that distance traveled, okay? And so our trick here is going to be to find KD and also to interpret our problem in such a way as we can figure out A and B, okay? So let's suppose we have this spring mass that has a resting length of 18 inches and it takes a force of 12 pounds to move the mass to a length of 26 inches. How much work is done to stretch the mass from a length of 20 inches to a length of 30 inches? So what we want to do, okay, is we're first going to think about this in terms of what our spring mass constant is. So we first want to find K, all right? We want to figure out what K is in order to give us that force equation. So what we're told is that it's going to take 12 pounds. So our force, f of x, will equal 12, or we'll call it f of x1, which is going to equal 12, okay? And we want to move the mass to a length of 26 inches. Well, the displacement here is actually going to be 26 minus 18, okay? And we should probably maybe call this f of d, all right? 26 minus 18, because this is how far we are going, and 18 is our starting position. So it ends up equaling 8. So what we do, we utilize this formula for the spring mass constant. We're going to get f of 8 is going to equal 12, and that equals K times 8. And when we solve that, we get K equals 12 over 8, which equals 1.5. So our spring mass constant ends up being 1.5. Okay? And that's just utilizing this simple equation, right? And this thing here is called Hooke's law. Force equals K times D. D is the displacement of the object. K is some kind of constant. Okay, the spring mass constant as we call it. So now what I have is I now have my work is going to equal some integral along some kind of interval of 1.5, okay, dx. 1.5, excuse me, 1.5, yes, 1.5x dx, right? Because that d is going to end up being my x. So 1.5x dx. Now we need to find a and b. Well, a is the smallest amount that we're going to displace, and b is the largest amount, top to bottom. So if we think about this, what we're going to get is our a is going to equal 20 minus 18. We're going to stretch our spring from resting 2 inches, that gets us to 20, and our b is going to end up equaling 30 minus 18, which equals 12. And so what we end up with is we end up with our function for our work. Okay? What we are doing, what we want to set this up, is we're going to set up our resting length as 0. Okay? And then we ask ourselves how much displacement past that resting length. So you're not going to like use 30 and 20. Instead, what you're going to use is you're going to use, in this case, 20 minus 18, 20 minus the resting length, 30 minus the resting length for those intervals. Okay? So once again, what we have here is we have a set of work problems, okay, where basically what we're going to do is we're going to take the force, all right, the force that's generated, use some kind of equation, some kind of physics that we know already about those forces. We will then take that dx over some kind of interval, right? And that interval is going to be dependent upon where we start, right? Our starting position. Okay, so what this does is that this gives you kind of an introduction to work, to kind of understanding work a little bit better. We're going to be looking at another problem I've added some videos to about pumping problems that you can use. And they're tricky. You've got to work through them, spend some time thinking about them. They might take you a little bit, but once you get them, they end up being not too terrible. Okay? All right, so this ends the lecture.